Hello, today we are looking at the 2015 AP Physics C Mechanics number 1. So this is actually a kinematics question, at least most of the parts of it are kinematics. And so let's go ahead and look at this question. So it says a block of mass m is projected up from the bottom of an inclined ramp with an initial velocity of magnitude v naught. The ramp has negligible friction and makes an angle theta with the horizontal. A motion sensor aimed down the ramp is mounted at the top of the incline so that the positive direction is down the ramp. That is important there, positive direction down the ramp. The block starts a distance d from the motion sensor as shown above. The block slides partway up the ramp, stops before reaching the sensor, and then slides back down. Consider the motion of the block at some time t after it has been projected up the ramp. Express your answers in terms of m, d, v naught, t, theta, and physical constants as appropriate. That's definitely something important to note, that you really need to pay attention when it's telling you to express your answers in a particular units. That's not optional, you must do that. Okay, so let's go ahead and look at AI. We got to determine the acceleration, and so the question is, what method would we use to determine the acceleration here? And if you think back to your physics toolkit, that should be, if we're looking for A, then we need to actually use forces. So we're going to go ahead and draw this free body diagram here, where we have mg straight down, we have Fn up perpendicular to the inclined plane, and then we have our axes here. Remember, we're tilting our axes. Mg needs to get split into those two components. So our blue component, which is into the inclined plane, and then our red component, which is down the inclined plane. So that red component is going to be what's actually pushing it down the inclined plane. And so that component is going to be mg sine theta. Remember, this is one scenario where x does not go with cosine and sine does not go with y. But in this scenario, mg sine theta is what's down the inclined plane. Okay, now the Fn and mg cosine theta are going to cancel out, so our Fnet is just mg sine theta. Now I need to actually solve for A, so I'll plug in for Fnet, so I have ma equals mg sine theta, and then I go ahead and cancel out our m's. Okay, and so my acceleration is g sine theta. So let's go ahead and look at part II. So it says determine an expression for the velocity v of the block. Okay, so we have AII. And for this part, there really is two different methods you could use. One, you could take the integral of our acceleration. Alternatively, we know that the velocity function v is equal to v naught plus at. Okay, and so that's maybe a little bit of an easier way to do it. So I just have v equals v naught plus at. And so I just need to plug in. I know my initial velocity is just v naught, and then I'm just going to plug in my a. Remember, I'm allowed to use that specifically because my acceleration is constant in that scenario. Okay, it needs to be constant though to use that formula. So I have something like v equals v naught plus g sine theta. I put parentheses here, t, just to make sure you can tell that the t is not part of the inside the sine. Okay, so that's the answer for that. You will notice though that the v naught is in the opposite direction. Okay, and so because v naught is in the opposite direction as acceleration, it needs to be negative. Now we know that the acceleration can't be negative because they say the positive direction is down the ramp. Okay, this is one where it's very easy to lose those points, and so this is why it's so important to read the question carefully to make sure if it says something about axes, right? We talk about axes, setting our axes. Make sure you're using the problem's axes, otherwise you can definitely get that problem wrong. Okay, so now we have AII, and so for this part it says determine an expression for the position x of the block, and so here we just need to find that position function. Okay, and so what we're going to do here is, once again, you could go ahead and take the integral of that velocity function, or you could also use a kinematics formula. So that would be that first kinematics formula, x equals x naught plus v naught t plus 1/2 at squared. You can kind of think about how you do that calculus, that integral, and you can see where that 1/2 the t squared is coming from. Remember, our initial position is going to be x equals d. our initial velocity has to be that negative initial velocity, and then our a is just going to be mg sine theta, just g sine theta, okay? So all we have to do is plug in those values and we get our answer. So we get x equals d plus negative v naught t plus 1/2 g sine theta t squared. Okay, and that would be the answer for AII. So hopefully not too bad. Remember, you could either use calculus or you could just plug in because the acceleration is constant in this case. Let's go ahead and look at part B. It says derive an expression for the position x min of the block when it is closest to the motion sensor. Express your answer in terms of m, d, v naught, theta, and physical constants as appropriate. So for this question, this one, hopefully you can determine, is another kinematics question. It would also be possible to use energy, but I'm going to show you how to use kinematics on this question. And so for a kinematics question, we really want to be thinking about what are the variables we know, okay? Kind of thinking about our scenario, right? And so we have this angle here, and we have this block. It's going to be traveling up to some point. We know that the problem says it's not going to hit the motion sensor, so it's going up, and it's going to come back down at some point, okay? And then at that point, it's going from a positive velocity as it goes up to a negative velocity as it goes down. And so at some point, at that top point, it actually needs to have a zero velocity, right? It's going in one direction, then it's going to go in the opposite direction. So at some point there, we need a velocity of 0. And this is a really important point for this question because it tells us that our VF, our final velocity, is going to be 0, right? We know that our initial velocity is just V naught. We're just going through defining our variables. That's an important step of a kinematics question, sort of getting that first part out of defining all our variables. So we get delta x equals x minus d, right? So our change in position is going to be our final, or our initial position, which is d, and then we have our x min. That's our smallest distance, and so it'll be x min minus d equals delta x. We know our a is still g sine theta, okay? And so in this question, we're kind of solving for delta x to solve for x min, okay? So we have 4 variables that we know, and then 1 unknown in there. And so we need to pick an equation from that. So this would be a great time to grab your formula sheet and go ahead and see if you can pick the correct formula. So we have a equals g sine theta there. And so we can go ahead and use the formula v squared equals v naught squared plus 2a delta x. So that formula fits those 4 variables, and we don't have any extra variables here. So we have 0 equals v naught squared plus 2 g sine theta times x min minus d. And so we're going to go ahead and solve for x min. So that's what we're solving for here. So we're going to need to kind of shift things around and solve for that variable x min, not just delta x. We actually do need to solve for all of x min. Okay, so we have negative v naught squared, so I move that to the other side, 2g sine theta, x min minus d. And then we're going to divide by 2g sine theta. So we'll have negative v naught squared divided by 2g sine theta equals x min minus d. And then I'll add d to the other side as my final step. So I'll have x min equals d minus v naught squared divided by 2g sine theta. Okay, and so, whoops, sorry about that. And so that's just x min, and that solves for it. Let's go ahead and look at part C. So it says, on the axes provided, sketch graphs of position x, velocity v, acceleration a as functions of time for the motion of the block while it goes up and back down the ramp. Explicitly label any intercepts, asymptotes, maxima, or minima with numerical values or algebraic expressions as appropriate. So we're really thinking about what will this motion look like. And so what you really want to do is go back to part A and look at those functions you came up with, right? I, and I, right? So we're looking at, obviously we're starting at that D spot, and so we want to label that because it does say label. And then we're going to approach 0, right? But we're not going to get there because we're only going to get to x min. And so this is going to be a nice little curve, and it's going to go down to x min and then go back to distance d, right? So if you look at it, the top value, right, that's labeled as x min. And so we'll be going up and then back down. Remember, our initial velocity is negative, so we want to be heading towards 0 because x equals 0 is at the top. We're not going to get to 0, we're just going to head to 0. Now we know it's curved because it's a parabola. As we saw for I, as that formula, it's a parabola. And then when we're looking at v, this is just going to be a straight line because we know that the derivative of a straight line is a curve. And then our initial velocity, as I circled there, is just going to be that v naught. Now remember, the v naught was negative, right? We have this negative v naught. So I've made a mistake here. You can probably point it out. It's not supposed to be starting at a positive number. It needs to be starting at a negative number. So it'd be negative v naught. And then it will be just traveling up to this top value. That is really important to make sure you have that negative v naught. And then our acceleration is positive. So that's why we have that positive slope on that graph. So really important to make sure you're keeping that negative constant because that's definitely an easy way to lose some points. And then our slope is going to be g sine theta. We know it's constant, so our whole acceleration is just going to be g sine theta, a constant value, okay? That's not changing at all. So those are our 3 graphs there. We can now go ahead and start looking at D. So after the block slides back down and leaves the bottom of the ramp, it slides on a horizontal surface with a coefficient of friction given by mu k. Derive an expression for the distance the block slides before slipping. Express your answer in terms of m, d, v naught, theta, mu k, and physical constants as appropriate. So this question, there's actually 2 different ways you could solve it. And so one way would be using forces and kinematics, okay? And so that way is definitely a good way to do it. We would set up our F net, we would find our acceleration, and then we would plug that acceleration into our kinematics equation. So we'd have an acceleration, and then we would have an initial velocity. So our initial velocity on the way back down is going to be v naught. So we'd have acceleration, initial velocity, final velocity is 0, and we would solve for delta x, so that distance that it's actually traveling. And that method will work well. It maybe is a little bit more difficult than the method I will use. So the method that I wanted to use here is actually using energy, okay? Both will work, but I think energy for me is a little bit easier. And so with energy, I'm thinking about how the work done by friction is equal to that initial kinetic energy that I'm starting with, okay? And so this style of question, I'll set up where I have KE is equal to the work, right? And so this is really just the EI equals EF, right? That work done by friction is going to cancel out all of the work. And remember, my initial velocity at the end is going to be v naught, right? So the same velocity heading up is going to be the same velocity at the same position on the way down, okay? Remember, that's v naught there on that graph. So I have 1/2 m v naught squared equals f times d, right? My formula for work is just f times d. I don't need a calculus definition because there's no changing force. So I have 1/2 m v naught squared equals, let's go ahead and look at a free body diagram. Not a great square there, but make a quick free body diagram so I can kind of figure out what this force will be equal to. Remember, my force here is Ff. In this case, Fn will be equal to mg because those are the only 2 forces in the y direction, so they cancel out. My formula for Ff, I just plug in, so I have mu Fn, and remember it's going to be mu k. It is important to use the exact same variable that they give you, and then I know Fn is equal to mg. You'll notice that I accidentally forgot the d, and I'll come back and add that d here, okay? M's cancel out as well. So I have 1/2 v naught squared equals mu k gd. And so I'm solving for d, so I have v naught squared divided by 2 mu k g equals d. Okay? And so that gives me the distance it will travel. This formula makes sense because the velocity will increase the distance, whereas the mu k will decrease the distance. Okay? And so that's my free body diagram. And I have F net equals FF, MA equals FF, and then go ahead and plug in mu mg, A equals mu g, so that would be my acceleration, mu kg. Remember, it is important to use that mu k. So I know my v naught equals v, so this is sort of how you would solve it using kinematics and acceleration, right? So I found my acceleration, I know v naught equals v naught, and then I also know that the distance is what I'm looking for, and then the other key thing is that my final velocity will equal 0. Okay, so my final velocity is 0 in this scenario. And so now I have 4 variables, and I'm thinking about what equation will match those 4 variables. Okay, so this second method is also a great way to solve it, and obviously delta x is another way of saying d. Okay, so you're thinking about what equation has those 4 variables and nothing else. And so it's a similar one we used already, so v squared equals v naught squared plus 2a delta x. V is 0, that's my final velocity, so I have 0 equals v naught squared plus 2, a is negative mu kg times delta x. Okay, and then I'm just solving for v naught, so I have negative v naught squared equals 2 negative mu kg delta x. The negatives are going to cancel out, and then I'm just solving for delta x, so I have v naught squared divided by 2 mu kg. Okay, and so I get the same answer regardless of what method that I use, and so that's great. If you could always try to do a problem in 2 different methods, but that's not necessarily super important to do because it's kind of a waste of time to do it in 2 methods. I'm just using both methods so you can kind of see the 2 different ways that it's possible to solve this. Okay, so now suppose the ramp has friction. The same block is projected up with the same initial velocity v naught and comes back down the ramp. On the axis provided below, sketch a graph of the velocity v as a function of time t for the motion of the block while it goes up and back down the ramp, arriving at the bottom of the ramp at time tf. Explicitly label any intercepts, asymptotes, maxima, minima, or with numerical values or with algebraic expressions as appropriate. Okay, so this is really asking if we understand what this graph is going to look like, right? And so I'm kind of just drawing a diagram here to kind of visualize what's happening. So on the way up, I want to, well, let me say it this way. I want to use a free body diagram because I want to show how the forces are changing on the way up and the way down, right? And so I'm going to go ahead and solve for my F net. So I'll go ahead and find, I have mg sine theta, that's down the inclined plane. And then I also have ff down the inclined plane. So my F net is going to be equal to ff plus mg sine theta. Oops, ran out of room there. Let me go ahead and rewrite that. So I have F net equals mg sine theta plus ff. Okay, so in this case, both are going to be pointing down the inclined plane, so I have an acceleration down the inclined plane. Okay, that's as I'm going up. Now, as I'm going down the inclined plane, let's go ahead and draw that free body diagram. So I still have my box, I still have my mg straight down, I have fn to the right, but now since I'm going down the inclined plane, my ff is actually going to be up the inclined plane, right? It's going the opposite direction of motion here. And so once again, I split mg into components. I have that blue part, which is going to be mg sine theta. In this scenario, though, my F net is going to be a little bit different. So my F net is going to be equal to mg sine theta minus ff. Okay, and so I know that my acceleration is going to be smaller on the way down and bigger on the way up. So a up will be greater than a down. Okay, and so when I'm thinking about my velocity graph, that's my slope, right? my initial slope is going to be bigger than my final slope. So I'm going to have two halves here, okay? And so I know that the initial slope is going to be steeper than my final slope. So I'm starting at v naught, right, because that's my initial velocity, and it's going to be going faster, so it has to happen in less than the half the time, right? Because it's moving faster at the beginning, right? Accelerating faster at the beginning, right? My slope is steeper at the beginning. And then it's going to have a lower acceleration, so a shallower slope here at the end. Okay? And so that point where it switches directions, going up and back down, is going to come before the halfway point because I have a higher acceleration at the beginning and a lower acceleration at the end. Okay? And so it really is important that that point is coming before TF divided by 2, and then you have those two different slopes. Okay? So make sure you're labeling everything as best you can. So labeling that initial velocity, it did ask for you to specifically label things. So make sure you're doing that. And thanks so much for going through this problem with me. Hopefully you were able to learn something, and have a great day.